For more than 100 years, physics has been haunted by this ghost, the vacuum. We've thrown our best minds at it, but our grandest theories just keep ending up in a graveyard. So the big question is, why do we keep failing? And what if there's a new idea out there that thinks it can finally succeed where everyone else has failed?
And that really forces us to stop and ask a pretty wild question. We look at empty space and we think, well, it's empty, a void, nothing there. But what if that's totally backwards? What if the vacuum is actually the most complex, the most fundamental, the most important thing in the entire cosmos? Just hang on to that thought.
Now, this whole quest to figure out the vacuum, it's not new at all. In fact, you could say it's a graveyard, just littered with brilliant ideas from some of the smartest people who ever lived. And here's the thing. Understanding why they all crashed and burned, well, that's the key to finding one that actually might work.
You look at the list, from old-school ether models all the way up to modern ideas like emergent gravity. The point isn't just that they failed. The sheer number of them, the body count, tells us something really important. See, they weren't failing by accident. They were all running headfirst into the same brick walls again and again and again.
And when you dig into it, you find out it wasn't just one single problem. Nope. These failures, they can all be traced back to 3 deep, fatal flaws that were baked right into their foundations. Basically, 3 mistakes that doomed them right from the get-go.
All right, so let's name the culprits. Here are the 3 big ones. First, the basic building block they used was just too simple. It didn't have enough degrees of freedom, think of that as independent knobs to turn, to actually describe reality. Second, they started with a really flawed assumption about what space even is. And third, well, the math they used just couldn't handle the tough stuff. Let's break each of these down.
Okay, so flaw number 1. This one was right in the foundation. Almost all these older theories were built on this thing called a single real scalar. The easiest way to think about it is this. It's like trying to describe the entire universe using just one single lonely number at every point in space. That number could tell you about, say, density, or it could tell you about potential, but it couldn't do both at the same time. There just wasn't enough information packed inside.
The analogy here is actually perfect. Using that single real scalar is like taking a black and white photograph of a rainbow. Yeah, you can see the brightness, you can see the shadows, you get some information, but you totally miss the color, right? The most important part. To describe reality, you need the full-color photo. You need something that can capture multiple independent layers of information all at once.
All right, flaw number 2. This one is less about the nitty-gritty math and more about a core philosophical mistake. See, most of these theories started with a really big assumption, that space and time are just a stage, an empty, passive container. And all the physics we care about, particles, forces, fields, they're just actors performing on that stage. But here's the question they never asked. What if the stage is one of the actors?
It's exactly like trying to understand the ocean by only studying the waves. You measure their height, their speed, their shape, but you never ever ask what the water itself is made of. And that's the fatal omission. These old theories were so focused on the actors, they never bothered to ask what the stage was made of.
And Matt brings us to the final nail in the coffin, the math. It was just too simple. Most of these models, they love these nice, neat, linear equations that are easy to solve. The problem? The universe is anything but neat and linear. All the really interesting stuff, the really hard problems, the crushing force of gravity, the bizarre collapse of a quantum wave, the Big Bang itself, all that is intensely nonlinear. So the math broke down at the exact moments we needed it the most. Not very helpful.
So, okay, we've got a graveyard full of theories, all killed by the same 3 flaws. It sounds pretty hopeless, doesn't it? Well, this is where the story takes a sharp turn. There's a new approach. It's called dynamic vacuum field theory, or DVFT for short. And it doesn't just try to slap a band-aid on the old ideas. It scraps them and starts over, building a new foundation from the ground up, specifically designed to avoid those 3 traps.
DVFT starts by asking a totally different, and I think much deeper, question. Instead of thinking of space and time and matter as all these separate things, it asks, what if they're not separate at all? What if they're all just different behaviors, different dances of one single underlying thing? What if it's all the same substance, just vibrating in different ways?
So, the billion-dollar question, how does it actually avoid those failures? Well, it tackles each of those 3 fatal flaws head-on, using a completely new architecture. Okay, let's start with flaw number 1. Remember the black and white photo? DVFT fixes this by completely upgrading its fundamental building block. Instead of that real scalar, which is just one number, it uses what's called a complex scalar. The music analogy is great here. The old theories could play one note at a time. Plink, plonk. DVFT can play a full chord. It has two distinct properties living together at every single point all the time.
Now, don't get hung up on the math on the screen. The equation itself isn't the point. What's important is what it represents. This one object, which we call phi, it has two totally independent parts, rho and theta. It's not one number anymore, it's two. This is our full-color photograph right from the start.
And this is where it gets really cool. Those two parts, rho and theta, they're not just abstract math. They have real physical meanings. So you can think of rho as the density of space, or maybe its stiffness, how much it pushes back when you try to change it. And theta, well, that acts like a tiny little internal clock, ticking away at every single point in the universe. And because it has both of these, the theory can naturally handle things that need density, like gravity, and things that need a clock, like quantum waves. It gets you both, for free. Okay, now for flaw number 2, the empty stage. DVFT just flips that whole idea completely on its head. See, in this theory, the vacuum field isn't in space. The vacuum field is space. Space and time, they emerge from the behavior of the field. It's not the stage, it's the performance itself. And this next point is really, really important. A lot of these theories of everything in the past, they tried to fight with quantum mechanics or replace it. DVFT doesn't do that. Instead, it starts from its own deep principles, this vacuum field, and it derives the laws of quantum mechanics. It shows you why they have to be the way they are. It's designed to explain, not to tear down. And remember, that third flaw, the simple math that broke down, well, by fixing that, by having a richer, more complex mathematical structure, DVFT can do something pretty remarkable. It can describe the universe on every single scale, from the tiniest to the largest, all from one single set of rules. And when you see it laid out, the result is, well, it's pretty stunning. You start at the atomic scale, and the behavior of that little internal clock, the theta part, naturally gives you all the weirdness of quantum mechanics. Okay, zoom out to our solar system. The field's rho component, its density, perfectly reproduces Einstein's general relativity. Zoom out again to the scale of galaxies. The way the vacuum field responds to huge amounts of matter can explain their strange rotation without needing to invent dark matter. And then, at the largest possible scale, the slow, gradual relaxation of the entire vacuum field over billions of years looks exactly like dark energy. 4 different scales of the universe, all described by one theory. That's the goal. But listen, a good story is one thing. For an idea to be actual science, it has to pass the ultimate test. It has to be falsifiable. You have to be able to prove it wrong. It has to stick its neck out and make predictions we can go out and test.
And this is where DVFT really puts its money where its mouth is. This isn't just some nice philosophical idea. It makes specific, concrete, testable predictions. For example, it tells us the exact size where quantum weirdness should just stop working. It predicts a very specific relationship between how fast the universe is expanding and how fast that expansion is speeding up. And maybe most importantly, it tells us exactly where and how its predictions should differ from Einstein's. It's basically an open invitation to every physicist in the world. Here, go try and break me.
And that really brings us to this final quote, which sums the whole thing up perfectly. It's not a retrofit of earlier theories, but a structural completion of them. In other words, it isn't trying to just slap some duct tape on a broken model, it's trying to finally add the missing pieces that were left out from the very beginning.
And all of this leaves us with a final, really profound thought. If a theory like this is even close to being right, it means that everything we see, every star, every planet, you, me, we're not separate things existing inside the universe. We are behaviors of the universe itself. So are we? Is everything? Are we all just temporary patterns, just complex vibrations, in one single, vast, invisible cosmic ocean?